Hello everyone and welcome back to Nunley Math for what I hope will be a relatively short video talking about arithmetic sequences. We are in the middle of our unit on linear equations and linear functions, and arithmetic sequences fits very nicely into that unit, so we're going to go ahead and talk about it here. By definition, an arithmetic sequence is an ordered list of numbers in which the difference between each pair of consecutive terms or numbers in the list is the same. So, if I were to say to you 5, 10, 15, 20, this would be considered to be an arithmetic sequence because you can see we're starting at 5, we grow 5, we grow 5 more, and we grow 5 more. Just so you're aware, these little symbols right here, the 3 periods in a row, are called an ellipse. That just means that just because I stopped writing the numbers out doesn't mean that the pattern stops, rather the pattern continues. So 5, 10, 15, 20, 25, 30. Now, it is relatively easy to just create a list like this and to continue the pattern on, but suppose I was interested in what happens way on down the list. So instead of wanting to know what the 5th or 6th number is, I wanted to know what the 50th or 60th or 100th number in this sequence would be. It's a lot of work for me to just sit here and one at a time count my way up to those higher numbers. Instead, it would be nice to have a rule or a pattern we could follow in order to calculate that very quickly. And that's where our linear equations or our linear functions come in. So what I've done is I've created a table very similar to the tables you've seen in the last several videos where we've put the position of the number as being our x or independent variable, and we've put the value of the number in that position as being our y or dependent variable. So if I said to you, what's the first number in the pattern, you could look at the number and say, oh, well, it's a 5. If I said to you, what's the second number in the pattern, you would say a 10, third number 15, fourth number 20, and hopefully after you've done this, you can predict that the fifth number would be a 25. Now, once we've got this into table form, we can actually treat this the same way we've been treating our linear patterns over the course of the last couple lessons. In other words, we're going to look and see we are growing by 5 each time. 5 plus 5 is 10, 10 plus 5 is 15, 15 plus 5 is 20, and 20 plus 5 is 25. We have this repeated addition. And we've discussed in the previous videos that repeated addition is the definition of multiplication. So rather than just writing 5 plus 5 plus 5 over and over again, in my middle column, I can represent this as a multiplication problem. So in position 1, I would say I have 1 5. In position 2, I would say I have 2 5s, 3 5s, 4 5s, and 5 5s. And you can see that in my center column, I'm always having a 5, but the number in the parentheses matches whatever I select for my x value. So I'm going to put x. The number in the first position will be 5 times 1. If I'm in the second position, it's 5 times 2. It's always a 5 multiplied by the position. And you can see that 5 times 1 is indeed 5. 5 times 2 is indeed 10. 5 times 3 is indeed 15. 5 times 4 is indeed 20. And 5 times 5 is indeed 25. So really, we don't need to add anything extra onto the end of this pattern in order to make it fit. It could just be 5 times x, or in this case, 5 times x plus 0, so that it matches our linear equation form. Now, in our previous videos, we said a linear equation or function is any pattern that has a starting point b and a constant rate of change, and we said that can be expressed as y equals mx plus b, where m is the constant rate of change. You can see right here, since I'm constantly growing by 5, my m value is going to be the 5. And b is some initial value or starting point. Down here, you can see that we are starting at 0. So this pattern starts at 0 and grows by 5 for every position. In our previous videos, we said that the way we can calculate this number without having to make the entire table is just to ask ourselves what would have been in position 0. Well, position 0 would be the number that plus the first 5 gives us a 5, so position 0 would be a 0. Therefore, our linear function is just y equals 5x plus 0. If I wanted to put this in function format, I could actually call this f of x equals 5x plus 0. It means the exact same thing. Notice, every arithmetic sequence can be written as a linear function, where you have a constant rate of change, and you have some additional or extra value that needed to be added on. Usually, we can spot that constant rate of change right here, and typically the starting value is going to be whatever the 0 position would have been. Notice the 0, notice the 5. Once you have your function, you can answer questions like this. Find the 30th number in the sequence. Well, I could go 5 plus 5 is 10, 15, 20, 25, 30. I could just count it one at a time, but what's easier is to say, well, if my pattern is y equals 5 times x plus 0, and x is the position, position 30 would be y equals 5 times 30 plus 0, or position 30 would have the number 150 in it. This is going to be a lot faster and easier than having to go through and list the 5th, 6th, 7th, 8th, 9th, all the way up to the 30th term. Hopefully, once you've got it in table form, you're already fairly comfortable with writing the linear function based on the values you see. If this is difficult for you, you may want to go back and watch the video just immediately prior to this and the one prior to that. If you feel pretty good with this, then I would recommend that you try this pattern. I'm going to assume that if you wanted to, or if you already felt comfortable with that, you would have already filled that in, and I'm going to keep going so that you don't have to sit here and listen to some dead space on the video for the next 90 seconds or so. Again, my table, position 1 has a negative 7, position 2 has a negative 14, position 3 has a negative 21, position 4 has a negative 28, and I can tell from this pattern that I'm growing, or actually I'm decreasing, going down by 7 each time, giving me the negative 35. That's down 7 each time, so I have a negative 35 as my 5th value. If I wanted to take this repeated addition plus negative 7 and write it as multiplication, I would say, well, negative 7 times 1 is the first position. Negative 7 times 2 is the second. 3, 4, 5. In other words, to find the value of the number in any position, I'm going to take negative 7 times whatever the position is. Now, we're fortunate in this example again because negative 7 times 1 is negative 7. Negative 7 times 2 is negative 14. These actually work all the way down. There's nothing we need to add to them. So our function is y equals negative 7x plus 0. Remember, you can figure out this 0 without having to look here and guess and check just by looking over here and saying, well, what would position 0 have been? Something take away 7 gives us a negative 7, so you would get 0, 0. Again, y equals my rate of change, it's going down 7, times x plus whatever our 0 position would have been. That's right here. Once you have the function, you can solve problems like this. Find the 50th number in the sequence. We always rewrite the pattern, substitute in the position we're looking for, and simplify. The 50th position would have the number negative 350 in it. Not too bad, right? The next couple slides are just more of the same. They do present little differences, so it is important that you at least watch through the end. If you feel comfortable with any of these, or you feel like you understand pretty well, I would recommend pausing the video, trying your method. If you feel like your method works, then just skip ahead in the video and see if your answer matches. If you get stuck, then pause the video or rewind the video and watch me do it. Again, I have my table. The first position is 11, the second position is 15, third position is 19, fourth position is 23. I should at this point be able to predict the 5th position. Hopefully you've done that. I happen to know the 5th position is 27 because I know I'm growing by 4 every time. So I'm going to take that plus 4, that constant rate of addition, that repeated addition, and I'm going to write that repeated addition as multiplication right here in the middle. The first position is 4 times 1, second position is 4 times 2, 4 times 3, 4 times 4, and 4 times 5. Now, that means no matter what position I'm going to be in, it's always going to be 4 times that position. So position 1 has 4 ones, but 4 ones does not equal 11. 2 4s does not equal 15. 3 4s is not 19. 4 4s is not 23. 5 4s is not 27. These are all incorrect, but they're incorrect in a very specific way. Can you see what it is? If you need to, pause the video and think about it for just a second. I'm going to go ahead and go. Hopefully you figured out that they are all 7 too small. 4 times 1 is 4. I need 7 more to get to the 11. 4 times 2 is 8. I need 7 more to get to 15. 4 times 3 is 21. 4 times 3 is 12, plus 7 is 19, and on and on. In fact, it's always going to be 4 times the position, plus you're going to need 7 extra in order to get the number to fit. The reason that you need that plus 7 is because the number that's in position 0 would be whatever number plus the first 4 gave us that first 11. Remember, the first position says I had a 7, and then I added a 4 to get the 11. The second position says I had a 7, then I added 2 4s. The third position is I had a 7, then I add 3 4s. There's your slope-intercept form of your linear equation, your starting point and your constant rate of change. Once again, if I wanted to find the number in any position, I would just say, here's my original pattern, put an 80 in for the position, and that gives you the value of the number in that position. Hopefully you're getting better and better at this. You're beginning to recognize some things that you did not see before. So you're going to try this next one on your own. Again, I'm going to pause. I would recommend pausing the video, try it on your own. I'm just going to keep right on going. Here's your table. Position 1 has a 220, and I'm going to do this faster this time because you already know those. Can you see what the pattern is? 220, 209, 198, 187. If you can, then you realize the next number is 176 because you're going down by 11 each time. Remember, position 1 is 1 negative 11. Position 2 is 2 negative 11s, 3 negative 11s, 4 negative 11s, 5 negative 11s. It's always negative 11 times the position number. But notice, negative 11 times 1 does not equal 220. I'm going to have to add something onto this to make it equal 220. And if I pick the right number, when I add it to each of these, they should all be correct. The easiest way to figure out this number is to look over here and say, okay, whoops, got that in the wrong order. It is plus 231, sorry about that. The easiest way to find that if you don't know what it is ahead of time, is to look at this and say, oh, I had a minus 11 here. So what would the 0 position be? Well, the 0 position would be 231 because 231 minus 11 is 220. I probably should have done this part before I just gave you the 231, but this is probably the process you are using so far. You're probably finding it here and then going back and realizing that would be the same thing here. As we get better and better at this, ultimately our goal is not to have to do any of this at all. Rather, our goal is to become familiar enough to realize that this is my constant rate of change and that this is my starting point. Negative 11x plus 231. Again, once we get really good at this, we ought to be able to just look at the pattern here, spot the negative 11 as the rate of change, and then realize that whatever would have been in the 0 position is over here. Once we reach that point, we don't have to make the tables anymore. It saves us a lot of time and effort. Suppose I were to ask you what position would have the number 0. This is a little different than the questions we were asking earlier. Again, pause the video and try that. I'm going to keep going. We know our pattern, but notice X is the position. I'm asked about the position. What I'm given is the value of the number in that position. I'm asked, what would X have to be to make my Y a 0? Make sure you're reading your questions carefully. Sometimes I will give you the position and ask you for the value. Sometimes I will give you the value and ask you for the position. It shouldn't make a huge big a difference if you get that number in the right spot. This is just a two-step equation. We learned how to solve this earlier in the year. We're going to use the property of equality to subtract to subtract 231 from both sides. Again, because we're getting better at that, I didn't show that. You really ought to show that in your work since you're still developing that skill. If I want to get rid of a times negative 11, the property of equality says I need to divide both sides by the negative 11, and you come up with a 21. The 21st number in the sequence is going to be 0. So I'm going to count down from here. 76, 65, 54, 43. That's really hard to do. But when you reach the 21st position, that's where you should hit the 0. Again, two more quick examples for you. You're doing these faster and faster. If you're feeling really brave, why don't you see if you can write the function or the equation just from this without doing the table, and then go back and fill in the table to see if you were correct. I'm going to keep right on going. I'm going to fill in the numbers that were given to me, and then I'm going to look to see what my constant rate of change is. Hopefully you realize that you should have a 2 in this position because we're counting up by 8 every time. Now, a lot of us probably got confused because adding 8 looks like it's making the number smaller, but notice when we're dealing with negatives, as the number gets larger, it gets closer and closer to 0 until eventually it crosses over to the positive side. Once I know this constant rate of change, I just fill that in, and I know my pattern is going to start with 8 times x. Now, of course, 8 times 1 does not equal negative 30. 8 times 2 does not equal negative 22. There's some additional value that I need to figure out here in order to make this work. Probably you're not doing that anymore at this point. Probably you're using our rule that says what plus 8, what plus 1/8 gives us the number that's in this first position. Hopefully you're doing that now instead of this, but I'm just going to go ahead and do it this way, since we should already be familiar with that. It is minus 38, or if you prefer, what plus 8 equals negative 30, the 0 term should have been negative 38. And there's your linear equation. And maybe I want to know what the 100th number in the sequence is. Notice I'm asking you or giving you the position. I'm asking you about the value of the number. Y equals 8x minus 38. Put in 100, simplify, and there you go. Now, I did just notice that this says rocket and tiles. That's kind of funny to me. This should be position and value. I often cut and paste these tables from other worksheets, and sometimes I forget to switch them. So this is position and value, just like it was on the previous slide. Don't let those labels throw you off. I'll go back and fix those in my notes as soon as we finish this video. One more. This will be the last one, I believe, that we look at today. Again, pause the video, try it on your own. See if you can do it without the table. Then use the table to check yourself. I'm going to do it the long way. Again, it says rockets and tiles. This should be position and value. The first position is negative 3, 2, negative 11, 3, negative 19, 4, negative 27, and 5, negative 35. If you got that negative 35, then you must have realized that you're counting down by 8 this time, down by 8, which means all of these should be negative 8 times the position. None of these give us the right value, so there's something we need to add on to the end here. Hopefully you realized what that is. It is a plus 5, because some number minus 8 had to equal negative 3. Well, that number had to be 5 because 5 minus 8 equals negative 3. There's your pattern. Y equals, this is your constant rate of change. This is your starting value. If I ask you for the 350th number in the sequence, you can pause the video and try that. I'm going to go ahead and do this, assuming you've already done that. There's your original equation. Substitute, simplify. And I'll put a fancy little box around it. And that's basically it. This is, here again, just another way that we can find to apply this idea of a linear equation. It is the same as the previous two videos, so hopefully you're starting to get more and more comfortable with this idea of a starting point here and a constant rate of change. We will spend a couple more days talking about it in my class to help you get better and better at this, but I think this is probably sufficient for today. As always, I do appreciate you taking the time to watch. Thank you so much for spending your time here with us. If you got something useful out of this video, make sure you hit that like button so we know about it. Make sure you ring that bell to turn on notifications because we have a lot more stuff to come here at Nunley Math. I wish you all the very, very best. You all take care of yourselves, all right? Bye-bye.